Great, good morning. Thanks very much. I suppose I could apologize to people who may have heard this talk before, but in the words of the English composer Vaughan Williams, if a thing is worth saying once, it's worth saying twice. Right? So you'll get to hear it again. Okay. I won't apologize. Okay, so yes.
Back up a slide.
What?
Back up a slide.
Question time for later. Later. I take that as a question for later. Okay, so talk vaguely in two parts. We're going to look at how to do infinite time Turing machines in the style of Kleene as a true higher type recursion. So Kleene in the late 50s and early 60s, and there'll be a list of papers in a moment, gave two ways to describe recursion in type n objects. Now, type 2 objects for us, which is everything today, are functions from bare space to integers. So we're only going to consider type 2. Kleene considered type n. And he gave two ways of describing this in a kind of an equational calculus, in a kind of traditional style of Kleene church and so on. And he also gave a description in terms of Turing machines arranged along well-founded trees. And the two papers, the two styles were interleaved in his publications. And it was the equational calculus that was taken up by other workers in the 60s and followed. And the Turing machine approach of putting Turing machines on nodes on a tree was not really much investigated as far as I can see in the literature. But what we're doing today is taking that Turing machine approach of Kleene's, but it will just replace Turing machines by ITTMs, nodes in the tree, and we'll just see what we get. So, quick overview of ITTMs, which we've already talked about. So, we enumerate the cells, and these are traditionally written out on 3 tapes. Doesn't matter, could be 1 tape. There's a head that is looking at the input tape, scratch tape, and output tape across a block of 3 cells. And it moves backwards and forwards in the usual way. And the key thing is the sigma 2 properties. The machine is kind of sigma 2 describable in a way, because the value of the k cell at time lambda, okay, so think omega if you want, is the limit of what's in the cells at the previous stages, for alpha below omega. So what this means is there is a 1 in the cell if the sum alpha such that for all later betas, there's a 1 in the cell. This is sigma 2, it exists for all. Otherwise, it's a 0. And the rest of the architecture of the machine can also be given expression in terms of sigma 2 constructions. So we have to say what happens at limit points. Well, this describes what happens to the cell values, which may have changed profinally often. And then you have to say, well, what happens, where's the head, what instruction is being looked at, and so on. But you can express these in sigma 2 ways as well. I won't do all those details. We'll say that the output of an ITTM, and remember that the programs here are just ordinary Turing programs. So PE just lists the Turing programs. What we've done is just tweak the architecture. So on an input X in Cantor space, will be on the input tape, it's going to be that Y on the output tape, the stable Y, if it stabilizes down to some value. Consider that to be the output. The machine doesn't have to halt. We could have said that, but this is more general. Right? It's just what's on the output tape. We consider the potential output. And in which case, we'll say the computation converges, down arrow. If it doesn't stabilize, then it's up arrow. So one can then go through all the usual paraphernalia for the Turing machine analysis. There are universal machines. You can then prove SNM and recursion theorems. There's a degree theory for the outputs of such machines here. And we can consider having oracles to the machine here. One might have a real number as an oracle, or one might have a whole set of real numbers as an oracle. And the obvious kind of questions that crop up is, well, if I start the ETH machine on a 0 and it converges in this sense, what are the collection of those convergent Ys? So it extends the ordinary Turing machine idea, and we'll just look and see, now we've got infinite time, what elements of Cantor space can be written out this way. Well, what kind is perfectly good mathematical question? What do you get? How long does it take to get it as well? How long does a machine run before it stabilizes, if it's going to stabilize, or run on forever? And a simple kind of Löwenheim-Skolem argument, if you like, shows that there's going to be some countable ordinal time beyond which the behavior of the machine is either stabilized or it's unstable, but it's kind of repeating in a loop. It's just kind of going on forever. It's only to the L0 many pictures of the tape that there are, so it's going to repeat from some point onwards. In fact, it's a countable ordinal from which it repeats. So there is a countable ordinal for which all programs, PE on input 0, are going to repeat. So what's that ordinal? So here's a version of the halting problem. What are those programs that converge? How complicated is that set? Okay, any questions? Okay, so the theory machine. So this appears in a paper with Sai in a workshop that was held in Bonn quite a long time ago now. And the idea of this machine is it's a very nice picture of how you can build a universal machine. Now, the operations of a machine, you can see, are absolute well, they're absolute delta 0 operations. So they're absolute to L, the constructible universe. So we can always think of a machine on 0 input as running in L, or if it's on input X, running in L of X. What the theory machine does is say that actually we can look at computations of this kind and compute codes and theories for levels of the L hierarchy. And we can do this, well, only so far, because the machine's only got a certain potentiality. But what the theory machine then does is just churns away. It doesn't stop. It just keeps writing theories and codes for the levels of the L hierarchy. And then at some point, it's going to have to loop back and keep just repeating itself like this. So again, what does this loop look like, and what kind of things are there? Well, this program, the theory machine, produces levels of the L alpha hierarchy. And again, a central feature, excuse me, of this is that when you're writing the sigma 2 theory out, it's not the sigma 1 theory. It's not if a sentence becomes true in the L hierarchy, it stays true. It's sigma 2. It can vary, it can go backwards and forwards. So you might have a sentence that varies backwards and forwards like this, and you ask what in the limit, some limit ordinal lambda, is that in the sigma 2 theory or not? Well, again, it'll be in the sigma 2 theory if there was some earlier alpha such that for all later things happen. So that's, again, it's a sigma 2 property here. And what you get, if you take just the simple lim-inf of the sigma 2 theory of L alpha, is something very close to the sigma 2 theory at the limit. In fact, this lim-inf is just uniformly RE. Sorry, the sigma 2 theory is uniformly RE in that limit theory T hat. These are sort of details that you needn't worry about really at this point. But so we can always extract the sigma 2 theory at a limit level, L alpha, from the limit theory. This is done in a uniform way. It's important it's done in a uniform way so that the machine can just uniformly run ahead in the way that it is designed to do. And that's what this says here. If you're in a level of here is the Jensen J hierarchy. If you're in a level of the J hierarchy where you've got everything is countable, then you've got the sigma 2 theory is uniformly RE and this limit theory. So from the sigma 2 theory, you can then get, well, the whole theory and then the whole code of the level alpha. Okay, so that's... Okay, so we get a code for a limit level L lambda, say, and its theory, and then we can continue. Right? And this is the comment I made earlier, that the operations of the machine are absolute to L. So, in a sense, this theory machine is universal because it's producing levels of L and codes for levels of L. But within that code for a level of L is also included the statements that the ETH program has got a certain value, or the ETH program has halted. So actually, if you know the codes for the theories of L, if you know the codes for the levels of L and their theories, you know about all the computations that are going on in L as well. It's just part of that theory. So it's a universal program. And this is, as Sai introduced in his talk, the notion of sigma 2 stability. Because of this sigma 2 property, if you look at the least zeta, which has got a sigma 2 end extension, L big sigma there, so zeta is sigma 2 stable in L sigma, these levels of the L hierarchy have the same theory. So by what we've been saying, the machines must be looping on empty input between L zeta and L sigma. The snapshots of the machine, the whole picture of the cells and programs and so on, that's all sigma 2 describable. So that is going to be the same picture of the machine at L zeta as at L sigma. So if it's reached this far, it's now condemned just to keep looping with periodicity big sigma forever. So this sigma 2 stable, least sigma 2 stable is important for the theory of machines here. So if there is going to be convergence of, say, the ETH machine, and I seem to have swapped to this notation, on some integer input m and 0, if it converges, it's going to do so by this time here. And the convergence, again, is sigma 2 statement. There is some gamma, such that for all later deltas, the output tape is the same. And on the other hand, if it's writing garbage and overwriting garbage all the time, then it's going to enter into this kind of loop between zeta and sigma in what it's producing on the tape. This garbage will repeat itself. And that loop has got this length, sigma. And by L sigma plus sigma, the whole process would have repeated. Okay, so here are the Kleene papers I mentioned. So 59 to 63. So here are the equational calculus papers, and sandwiched in the middle of the two papers on doing the things in Turing machine format. And I guess, I mean, I don't know, but I guess, obviously everybody knew that for ordinary Turing machines, there's kind of equivalences between the equational calculus and the Turing machine picture and then other machine pictures. So I guess he was kind of bolstering his finite type theory by giving two presentations of it, through an equational calculus and through Turing machines. It's given up the ghost. Okay. So I'm going to jump straight in and look at what just now type 2. So these are functions that go from bare space to integers. So we're going to look at what the the ETH program does, given such a function f from bare space into integers, on input an integer m and a real x. So big lambda here indicates the level, perhaps, at which the machine is operating. This is nu 0, nu 1, nu 2. These are nodes which a machine is being called into action. And here's a little tree that describes my rather bad picture up here. So the horizontal bar is time, starting from 0, going off in this direction. And I draw this little hook to mean that this ordinal L, this zeta, is sigma 2 substructure of this L sub big sigma. The hook means a sigma 2 stable pair. So the machine trundles on at the top level, and at some point it's allowed to call for a subroutine. And it makes a query, and it says, does the E1th machine on input M1, X1 converge? If so, and it converges to some Z1, what it's going to receive back is the functional that it's being recursive in is going to receive a value, integer value, f of Z1 back. And once it's received that, then it can continue along that top horizontal. Yes? It does. They're all the same.
Is it the same oracle if?
Yes, it's the same f. So, as was just asked here, it may query down here, and of course this computation may itself issue a query in the same way. And it queries, does the program E2 on input M2, X2 stabilize, and if so, if it stabilizes to Z2, f of Z2 is then returned up here. And again, I indicate that this may take a computation from this point onwards up to its next sigma 2 stable pair to find out. That's how far we have to go to see whether it's converged or not. So, okay, so then information is passed up from nu 2 to nu 1 to nu 0, and then this continues like this. So the final outcome is what happens at the master computation on the top. The Z's are the outputs, putative stabilized outputs of the E1th machine acting on input M1, X1. So if that converges, exactly, yeah. So it's asking this question: does E1 on M1, X1 converge? And if the answer is yes, and it converges to Z1, then f of Z1 is returned. Yes? Then we have divergence. And the process is, yeah. So, as you can imagine, we can have divergence because one of these subsidiary computations doesn't converge, in which case there's nothing to present to the oracle F, and the whole thing is over. It can crash because the tree may be simply ill-founded. There's two ways it could not work. It could diverge, or it could just keep issuing lower and lower calls, which never get answered. So we're looking at well-founded computation trees. So for Kleene, in his type 2 recursion, he had that the trees were all hyperarithmetic. So you can then tell, well, the ranks of those trees are all less than omega 1 ck. Here, of course, we have much more complicated trees. But again, well-founded trees are the ones which give us some output. Okay. This is the basic functional called 2E in the higher type recursion theory. It's sort of an existential quantifier, and it does the very simple job of you put in an element, a bare space here, and it gives you a 1 or a 0 if that hits. That real is 0 somewhere or other. Y of k is 0. So this is kind of a base case functional, which we'll just work with, right? Simplest possible function you could think of in this context. And so again, you could ask, what is the halting problem in this simple functional? And again, how long does it take for a computation to diverge or converge? So now we've got trees of computations with all of these levels with sigma 2, extendability, hooks and things on. So the whole thing is very large, big process. If you take a functional G, you've got all sorts of nice things you can work through. The generalized recursive function theory, and so functions which you could define by these machines, these are closed under functional substitution. There are universal semi-recursive in G sets, the whole shoot, right? That you could imagine for ordinary high-type recursion theory we have here as well. No, halting is a special case of convergence.
Right, but
yes.
So you want to use the notion of convergence throughout.
Yes. Correct.
To change.
You could rejig it if you wanted. I think so. I mean, I think the machines are it's kind of natural to just let the machine run and the output's what's on the output tape. Even if the machine is footling away on its scratch tape doing something silly.
In the least.
Yes. It really emphasizes, I mean, somehow the central feature of the machines is this sigma 2 gap, this sigma 2 stability. So I prefer convergence to mean output tape converges. Okay, so what comes next, looking forward to a proof about pi 0 3 determinacy, is this idea of nesting. So when we go up the L hierarchy, we reach a point where some zeta is sigma 2 in some L sigma. Then we go further, we reach another point like that. Then after a while, these points, of course, will bunch up. So you're going to have a sigma 2 extendable ordinal that's a limit of these sigma 2 pairs. This is by elementary reflection. These sigma 2 elementary extendable pairs will be sitting inside the next hook. So we've got nested ordinals. So this is a 3 nested ordinal alpha. So this is supposed to be the L hierarchy growing from left to right. So there is a sigma 2 extendable pair, L zeta 2, sigma 2, and L sigma 2 here. But actually that is over-nested by another sigma 2 thing. When you get this in, and that's over-nested by a third pair, like this. This is a 3, alpha is 3 nested because it's inside 2. 3 nested links like this. Okay? What we'd like to have for the proof of pi 0 3 determinacy is an omega nesting. Of course, it doesn't exist, right? Because what would an omega nesting mean? You'd have to have an infinite descending sequence of ordinals, right, to give yourself an omega nesting like that. So you can have this, but of course only in ill-founded models. So actually, it then comes down to looking at places which can be omega nested in this sense. Right? Alpha here is omega nested. We're thinking of this alpha as sitting inside the well-founded part of a non-well-founded model N here. And in the model N, there are these sigma 2 extendable pairs. L zeta 0 is sigma 2 in LS 0. S is just an ill-founded ordinal. And L zeta I is sigma 2 in LSI, again in the ill-founded part of the model. So you could create these omega nested phenomena by looking at ill-founded models. So the question is, again, where can you get in the L hierarchy? Where is it sufficiently rich in the L hierarchy to find an alpha which supports a kind of infinite nesting like this? I mean, alpha can't be omega 1 ck, right? That's far too small, right? You can't have these sigma 2 extensions around such an alpha. But you can show that there are such alpha. You just have to go to alpha that's, let's say, well, an upper bound here is a beta which is sigma 2 non-projectable. So where the reals are a delta 1, I get the numerology wrong, a delta 1, 3 model of comprehension. So you have to go a distance, right, to find such alpha, but it's easy to argue that they exist. So the next lemma is a little bit more technical. They're about the lemmas you need to prove to see what's kind of going on, right, in such a situation. So again, we'll just stick with recursion in this very simple functional 2e. I mean, everything works for other functionals. It's a very general theory. So lambda here was this level function. When lambda is 0, then you're at the master computation at the top. Then you might be at level 1, 2, 3, n. So this is sort of a little bit of bookkeeping. It's saying, suppose alpha is one of these n-nested ordinals in the L hierarchy. Then the program is not yet exhibiting final looping behavior, only if the level is greater than or equal to n. It's sort of just a bookkeeping function. Right? If the level was strictly less than n, we would know that it's already trapped in a final loop. Just take it from me. Okay, now comes the least infinitely nested ordinal. This is now important, and I'm calling it beta 0. Bit of unfortunate choice there, but anyway, it's beta 0. It means that there's an ill-founded model M whose well-founded part is this L beta 0, and it supports this picture of this nesting. One can show that this is sigma 1 non-projectable, so actually there's a least alpha 0 bar, which is a sigma 1 substructure of this L beta 0. Just how it looks. So then the lemma says that any computation at all on some integer input, if it's not already convergent or divergent in the sense over there, right, here, then the ill-founded tree, it's got an ill-founded tree, it's going to crash. It's telling us every computation is either going to be convergent, divergent, or crashes by time beta 0. So that's the black hole, as it were. So everything is over, effectively, by then. Alpha 0 bar is a bit like, it's the event horizon. So if something is going to be a good computation, well-founded tree, it's going to be convergent or divergent by this smaller ordinal alpha 0 bar. Once the computation has gone beyond that point, and it's not yet convergent or divergent, it's doomed. It's going to crash. Right? So it's gone over the event horizon and it's going into the black hole, and it's going to crash. So the interesting stuff happens, well, cofinally in this alpha 0 bar, and then the trees will carry on being well-founded, but the computation is doomed to become ill-founded by stage beta 0. So this is half an hour, right? This is the application to sigma 03 determinacy. So, I mean, it turned out, I mean, it's sort of the way into this idea of omega nestings was through the proof in Martin's circulated book of sigma 03 determinacy. If you analyze carefully enough what's going on, one can make up games that are related to producing, Friedman-like games that are producing levels of the L hierarchy. And you can see you can do this all the way up to this alpha 0 bar. So the least beta, such that every sigma 03 game has a winning strategy definable over that level, is also this beta 0. So for player 1, it turns out, again, there's always this difference between where player 1 and player 2 sees their strategies. For player 1, the strategy will occur before or at this event horizon. For player 2, the strategy is definable over the black hole, L beta 0. So there's this gap between where player 1 and player 2 strategies occur. And it's this beta 0. Okay. So this beta 0, right? I mean, I've sort of let the cat out of the bag by saying this is indeed what's going to happen. So the conjecture is that this beta 0 is the least ordinal, such that every machine is convergent or divergent before beta or crashes at time less than or equal to beta 0. So I want to then make a comparison with what Kleene, Moshevarkis, and other people did. K here is for Kleene, again looking at the Kleene type 2 recursion. The halting problem here is recursively isomorphic to the sigma 1 theory of L omega 1 CK, which is recursively isomorphic to Kleene's O, complete pi 1 1 set. And it's also recursively isomorphic to a complete G sigma 0 1 set. So what this means here is you take a recursive listing of all the sigma 0 1 games, open games, present them recursively, and you look at those games that are won by player 1. That's the complete G sigma 0 1 set. And that's recursively isomorphic to all of these things. So there's one of this big list of things in Kleene's O. Okay, so the conjecture here is that this halting problem in our setting, right, is recursively isomorphic to, well, what? Well, the sigma 1 theory of this L beta 0. And it's recursively isomorphic to a complete G sigma 0 3 set. And indeed, this is what happens, right? These things are both true. Yes, yes, in a recursive presentation of sigma 0 3 sets, yeah. It will do, yes. Yes, that's the case.
The sigma 1 theory of
Exactly. Exactly. Okay. Sorry if I did start a few minutes late, but I suppose in a sense it was my fault. How is this going to work? So we'll formulate a condition, a pi 1 condition, and a special program, PE0, is designed to never enter a final loop, right? And it's going to crash at stage precisely beta 0. We want to find a program that stretches the limit. And as in a theory machine, it's going to write out codes for levels and theories of L, and it's going to search for sequences of a certain type, increasing length, in longer initial segments of the L hierarchy. And the sequence would satisfy phi. At stages alpha that are n-nested on the way up to finding this ordinal that supports the omega nesting, it's going to operate at levels lambda greater than or equal to n, at depth n. So the idea is, the intention is, when it reaches this beta 0, where there's an omega nesting available in an ill-founded end extension, the operation of the machine is being forced further and further down a tree. And so at beta 0, that tree is ill-founded and we crash. And we're looking for approximations. And essentially what you want to think of is this k plus 1 tuple is an approximation to k plus 1 ordinals zeta I, which are beginnings of sigma 2 end extensions. We're trying to look for the lower ends of those hooks. And it may be that we search for the lower end of these hooks and they look good for a while, but then some sigma 2 thing falsifies it. And we may have to throw away this approximation, and then we go back up through the machine, through the tree hierarchy, in order to continue the computation with a bit that still looks good. It's a search. We're looking for a search. We're looking really for an omega sequence of initial segments of sigma 2 substructures in an ill-founded extension of, well, somewhere, whenever I reach it. That's what the program is doing. And one does this through a bar-wise consistency argument using L alpha logic for admissible ordinals alpha here. Let's just see what you might have here. You might have a sigma 2 extendable pair, so L xi, sigma 2, and L sigma. Then you can show, so the theory, the idea here is, when you search through the L hierarchy for a beta model of a theory, being a beta model is, it's a nice, well-founded model. You might have to go a certain distance to find that. But actually, before you get there, you're going to find models of that theory which are ill-founded. So you can look for models of a theory, and maybe they occur low down. A model of a theory with a certain well-founded part, and you continue. But for a beta model, you may have to look further through L. So what we're doing is looking for approximations to some beta model of a theory, but which is perhaps a bit further along the way. But if I've got a sigma 2 extendable pair, actually there is a T0 below this psi. So this T0 looks like it could be the initial segment of a sigma 2 extendable pair in an ill-founded model. Indeed, it is such, right? So there is a T0. So for all admissibles from this T0 up to this sigma, T0 is the initial part of a hook. It's sigma 2 in some ordinal in some ill-founded end extension. So, but to see whether phi and alpha holds of this T0, you only have to go to the next admissible set beyond L alpha to see whether this theory is consistent and so on. It's just a search. So that's just a case for one thing here. And this complicated looking statement is saying the same thing, not just for T0, but for a k plus 1 tuple. So no need to overlook at that. That's a proof of that, which we'll admit. This is the statement I referred to earlier, that alpha 0 bar is an event horizon. If you've got a k plus 1 tuple, and with sigma 2 extendable to these ordinals here, then gammas right here below zeta k up to sigma k, you're forced to be below depth k. So if you're in a nesting, you're forced to be roughly at that depth, how big that nesting is. So the program never reaches an overall looping pattern, and it crashes at this stage, beta 0. And this is the same alpha 0 now rewritten. Alpha 0 is the least alpha bar, which we've got as a sigma 1 substructure, this L beta 0. So no computation is convergent in that in this interval here. So the picture that I was describing is the true picture. And so finally here, various characterizations then of this ordinal beta 0. These are equivalent. It's the least ordinal that supports this omega nesting. I'll skip to 3. Any strategy for sigma 0,3 game is definable over this L beta 0, and there's no ITTM generalized computation here computes for more than beta 0 stages. Very nice result of Hackman was he inserted 2 into this here. He showed that the elements, the reals in L beta 0 are a model of pi12 monotone induction. In fact, it's the least model of pi12 monotone induction. So this kind of gives another backing for this idea of nesting here. And indeed, he showed that in many places, ordinals that support omega nestings give you these models of pi12 monotone induction. It's an open question as to whether every nesting gives a model of pi12 monotone induction. And so he showed in his paper 1 implies 2 implies 3. Okay, and we get what we want down here. The halting problem for this generalized high-type recursion indeed gives us, essentially is the sigma 1 theory, this L beta 0, and essentially is this complete G sigma 0,3 sigma 0,3 set. Fine. Thank you. That's all. This should say thank you.